Every motion in the universe, from falling apples to orbiting planets, comes down to one thing: forces. In today's video, we'll explore how forces cause motion and how Newton's laws help us describe and predict that motion. We'll start with gravity, the most familiar force, and move into applied forces such as tension, normal force, friction, and more. We will solve problems involving Atwood machines, elevator problems, connected mass problems such as sliding horizontally and objects being dragged up an incline or ramp. So let's start by describing Newton's three laws. The first law deals with inertia. An object at rest tends to stay at rest, while an object in motion continues in motion along a straight line unless otherwise acted upon by an outside force. So if you were in outer space where there's very little forces, and you were to throw a baseball, it would travel in a straight line forever until some other force reacts with it. Newton's second law is the relationship between force, mass, and acceleration. So acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. Newton's third law: for every action, there's an equal and opposite reaction. Forces always occur in pairs. For example, if I have a table and I place a book on this table, the book is pressing downward and the table is pushing upwards. If they're equal, then the book doesn't move. But if the book is pressing harder than the table is pushing upward, then the book falls to the floor. Or if you're swimming, you're pushing the water backwards to move forwards. Same thing. Newton's law of gravitation, this explains how gravity works throughout the universe. Okay, so Newton's law of gravitation says that this gravitational force is equal to G m1 m2 divided by r squared, where G is a gravitational constant and it's equal to 6.67 times 10 to the negative 11th power. The M1 and M2, these are the mass of the two objects in kilograms. The R is the distance between the centers of the two objects. That will be in meters. Oftentimes, you will need the mass of the Earth, 6 times 10 to the 24th kilograms, or you can say 5.98, whichever you like. The radius for the Earth, 6,370 kilometers. So you have to convert that into meters, of course. And the distance to the sun. Okay, that would be 1.5 times 10 to the 11th power meters. So this would be 6.37 times 10 to the 6th power meters. You ever wondered why you weigh more in an elevator when it's accelerating upward, or you feel much lighter when the elevator is going downward? Well, let's try to explain that. If this is an elevator, and this is a person in the elevator, Okay, suppose this person is standing on a pair of scales and the elevator is moving upward. The push on the scales minus the weight is equal to the mass times acceleration. If the elevator was going downward, then your weight is greater than your push. So we're going to say that the weight minus the push is equal to mass times acceleration. If I have an object and I have a rope attached to it, okay, this rope is applying tension. This tension is going upward, okay, so the tension is going this way. But the weight of the object is going downward. So if it's not moving, then the tension and the weight are equal to one another. But if it is moving, then we can say then that if it's going up, we can say that the tension in the rope is greater than the weight and if it's moving down, we can say that the weight is greater than the tension. So it's essentially, we'll use this concept over and over again. Okay, an Atwood machine is essentially a pulley and we have an object suspended on both sides. I always put my larger object on the right side. Therefore, my pulley always turns clockwise. I'm going to call this mass 1, and this is mass 2. The tension here is going upward. This tension is also upward. We're going to be using the formula force equals mass times acceleration. On the left side, since it's moving upward here, I'm going to say that tension minus the weight is equal to the mass times acceleration. On the right side, it's moving downward. So we'll say the weight minus the tension equals mass times acceleration. Okay, so I'm going to put weight for object 1 here, the mass of object 1, the weight of number 2, and this will be the mass of number 2. The tension should be the same, and the acceleration should be the same. So let's add these two together. If I add these two together, you'll notice that I have a positive tension. It's going to cancel with this negative tension. So this gives us the weight of object number 2 minus the weight of object number 1 is equal to the mass of the first object plus the mass of the second object times acceleration. So this is mass of the second object times gravity minus the mass of the second object times gravity equals m1 plus m2 times a. So I could simplify this into m2, that's a 1 there, sorry about that. So m2 minus m1 times g over m1 plus m2, that's equal to the acceleration. So that's the formula we'll use for acceleration. Once I get my acceleration, then I can plug it into either of these equations, and I can solve for the tension. Okay, the next type of problem is if I have a mass it's connected going across to a pulley and coming down like this. For mass 1 and mass 2. The weight is my force pulling it downward. So my weight here is going to be equal to my applied force. Let's assume that this is a frictionless surface. It gets a little more complicated when we add friction. That'll be for a later video. If we say that force equals mass times acceleration, the force will be the weight of m2. Both masses must accelerate, so it'll be mass 1 plus mass 2 times the rate of acceleration. The force is mass 2 times gravity we can say then acceleration is mass 2 times gravity divided by the sum of the masses of mass 1 and mass 2. The last example, I have a ramp and on this ramp I have an object. Very similar to the last problem. This is mass 1. This is mass 2. This is the angle of the ramp or the triangle or whatever. Okay, so I have weight going here. This is equal to my force. Tension minus weight equals mass times acceleration. And the same thing here. Weight minus tension equals mass times acceleration. So we're going to say that mass 2 times gravity minus the tension is equal to mass 2 times acceleration. For the one going upward, we'll say that's tension minus mass 1 times gravity times the sine of theta equals mass 1 times acceleration. Again, if we add these together, the plus t and the minus t cancel. So we'll have mass 2 times gravity minus mass 1 times gravity sine theta equals mass 1 plus mass 2 times acceleration. So we can say then the acceleration is equal to mass 2 times gravity minus mass 1 times gravity sine theta over m1 plus m2. Our first sample problem, a 600 Newton object, is to be giving an acceleration of 0.70 meters per second squared. How large of an unbalanced force must act upon it? So if I just draw it like a little cart here. Okay, so this is the applied force. This is the force due to friction. It's weight, which is a force going this way. And in this direction, we have the normal force. So this unbalanced force here will be the applied force minus the frictional force. But let's not include friction in this problem here. So we know that force equals mass times acceleration. Okay, so the force is equal to the mass. This is not mass, this is weight. So I need to convert this weight into mass. If weight equals mass times gravity, then mass would equal weight divided by gravity. So if I say 600 divided by 9.8, that will give me the mass. So I'm just going to plug that up here. 600 over 9.8 times the acceleration of 0.70. Therefore, my force must equal 42.9 newtons. This will be the amount of force in excess of friction that would cause it to accelerate at this rate. In the next problem, I have a cord passing over an easily turned pulley, an Atwood machine. Okay, it has 7 kilograms hanging from one end and 9 on the other one. So I can put my 7 kilograms here, my 9 kilograms here, because I always want my heavy one on the right side, so it will rotate clockwise. So this side will be T minus weight equals mass times acceleration. This side will be weight minus T equals mass times acceleration. Okay, so let's go ahead and say T minus weight 1 and weight 2 minus T equals M2 times acceleration. So weight 2 minus weight 1 equals M1 plus M2 times A. So A is equal to weight 2 minus weight 1 Okay. So the weight 2 will be 9 times 9.8. Weight 1 is 7 times 9.8 divided by 9 plus 7. This will give us an acceleration of 1.225 meters per second squared. All right, to find the tension, let's take one of these equations. For example, I'm going to take this top equation here. I'm going to bring it down. I'm going to substitute the values. So T minus weight 1, where weight 1 is 7 times 9.8, equals 7 times A, where A is 1.225. So this tension here is equal to 77.175 newtons. So we were able to solve for first acceleration, and then we can solve for tension by substituting. In this example, I have a 700 Newton man standing on a set of scales on the floor of the elevator, and the elevator is accelerating at 1.8 meters per second squared. So what is the reading on the scales? Okay, so we know that if you're going up, it's the push minus the weight equals mass times acceleration. So I'm going to say this push then is equal to mass times acceleration plus the weight. All right, so his mass, again, this is 700 newtons. I need to convert that. So I'm going to say 700 divided by 9.8, that's his weight, times the acceleration, which is 1.8, plus his weight, which is 700. This will give us 828.6 newtons. That will be the reading on the scales. All right, we have a toy truck sitting on a surface. It's to be going off the edge. So this truck is 35 kilograms. This is 4.6 kilograms. So when this mass is released, I want to know what's the resulting acceleration of the truck. Remember, this is the weight. The weight is going to equal the force that causes it to accelerate. So the force is equal to m1 plus m2, because both objects are accelerating. So the force is 4.6 times 9.8. So the mass of two objects will be 35 plus 4.6 times A. So A is going to equal, I think this is 45.08, and this is 39.6. So I can say the acceleration then is equal to 45.08 divided by 39.6. So acceleration is equal to 1.14 meters per second squared. In this example, I have a rifle bullet leaving the muzzle of a gun at 800 meters per second. So when it gets to here, it's going to be going 800 meters per second. The barrel of the gun is 80 centimeters long, and the mass of the bullet is 20 grams. So what force is needed to accelerate this? We know the formula is F equals m times A. Okay, I need to find the acceleration. So let's go back. We learned that the final velocity squared minus the initial velocity squared is equal to 2 times 8 times d. So the final velocity squared minus the initial velocity squared divided by 2 times the distance will equal the acceleration. So we have 800 squared minus 0 squared, since it started from rest, times, it has to be in meters, 0.8 meters. So I know the acceleration is going to be 400,000 meters per second squared. All right, so if we have acceleration now, we can go up here and solve for force. So force is equal to the mass. This has to be in kilograms. So that would be 0.020 kilograms times 400,000. This gives us a force of 8,000 newtons. This problem, I have 2 bowling balls. Each having a mass of 6.8 kilograms. 21.8 centimeters apart. What's the gravitational force between them? So we'll be using F equals G M1 M2 over R squared. So this would be 6.67 times 10 to the negative 11 times 6.8 times 6.8, or you can say 6.8 squared, divided by the distance between them squared. This has to be in meters, so it's going to be 0.218 squared. I'll say that the gravitational force between those two objects is 6.5 times 10 to the negative 8 newtons. What if I brought the balls closer together? So maybe instead of 21.8, I was half that distance. What effect would it have upon the force of the gravity? Well, the law of inverse squares says, since this radius here, if I make that 1/2, then 1/2 squared is 1/4, and dividing by 1/4, which means it will multiply the force by 4. So if I brought the balls half the distance apart, the force will be 4 times the original force. Likewise, if I move the two objects twice as far away, the force of attraction will be 1/4. If I move them 3 times as far away, so on and so forth. That's the law of inverse squares. I have a rope that's guaranteed not to break as long as the tension on the rope does not exceed 450 newtons. So what's the greatest upward acceleration that can be given to a 42 kilogram mass without breaking the rope? Okay, so tension cannot exceed 450 newtons. This is a 42 kilogram mass. Since we're going to be moving upward, we'll be using the tension minus the weight equals mass times acceleration. So the tension here is 450 minus the weight, which is going to be 42 times 9.8 equals the mass, which is 42 times A. So I have 38.4 equals 42A. So A is equal to 0.91 meters per second squared. So that's the maximum rate of acceleration before the rope breaks. We have a ramp elevated at a 30-degree angle. We have a 5-kilogram mass on it. It's attached to a 6-kilogram mass overhanging. Let's solve for the acceleration of this. Okay, earlier we derived the formula that acceleration is equal to mass 2 times gravity minus mass 1 times gravity sine theta divided by m1 plus m2. So we can say the acceleration then is going to be equal to 6 times 9.8 minus 5 times 9.8 sine of 30 degrees over 5 plus 6. Acceleration is going to be 3.12 meters per second squared. From falling objects to elevators and pulleys, every motion comes back to one key principle. The net forces cause acceleration, whether it's gravity pulling us down or tension lifting us up. Newton's second law connects them all. In a later video, we'll take this a step further by adding friction and circular motion into the mix. Until then, thank you for watching. Please hit the like button and subscribe. Thank you.